All right, we're going to run through the solutions for your group test for tomorrow. So the first one, we're just checking to see if this equation is a solution for this differential equation. Notice we have the first derivative as well as the second derivative. So I have to take the derivative twice for my original function. First derivative, we've got chain rule. Derivative of e to the 3x is e to the 3x, and then we multiply by that derivative of the exponent. And then same thing for that second derivative. So I took this 3, chain rule, multiplied it by this 3 to get 9, and then the derivative of e is e. Summing those in, second derivative was 9e to the 3x plus 2 times that first derivative of 3e to the 3x. And does it equal 15 times y? So I subbed my y equation in as well, and then simplified, so multiplying the 2 times 3, and then combining like terms, and this one did check out. Second equation, there's a lot that we have to find before we can actually answer the question. Two unknowns, the k value and the initial amount. So first I used that half-life time. So the time that it takes for this to decay to half of its original amount, subbing those in and then solving for k. Taking the natural log of both sides, it will cancel that e, and I get my 24,100 times k out of the exponent. And then I divide both sides by that 24,100 to get my k value. As a reminder, these k values are really small, so keep 3 significant figures. Using that k value in the general equation, that y equals c e to the kt, subbing in what we know, how much is left after 1,000 years, that was that second sentence. So what I did to solve for c was divide by this expression, e to that power, and that's what I got for my c value. As a reminder, when you're rounding, round to 3 decimal places, unless you're talking about something like money where you round to 2 decimal places, or something like people or bacteria that can't be divided and then round to the nearest whole number. But in general, give me 3 decimal places. Finally, we have enough information to answer the question. So we use our equation y equals initial amount, which we just found, times e to the k value. And then the question was after 15, error. Okay, so this says 15,000 years. I did 15,100. So I will update that on the answer key. Question 3, solving the differential equation. So I did 2 things at once. I replaced my y prime with dy dx, and then I multiplied by dx to separate my variables. You must show the step where you're separating your variables to get full credit for these equations. To solve, we integrate both sides. I've got my u substitution. I let my u equal the entire denominator, took the derivative, solved for, in the numerator, I just had the x dx. So I took that 1/2, multiplied it on the outside, integrated that dy over here, and then we just have 1 over u du. So the integral of that gives me the natural log. Don't lose your absolute values. Always, always, always put your absolute values with natural log when you integrate. In this case, when I subbed back in, 1 plus x squared is always a positive expression. So then I can drop those absolute values if I choose. If you leave the absolute values, that's fine too, but I need to see them initially when you integrate with a natural log. Question 4. Same process, we've got to separate those variables. So I subtracted x squared from both sides and then multiplied by dx to separate my variables. Integrating both sides, this is just using our power rule. So adding 1 to the power and then dividing by that power on both sides. Now in this case, there's lots of different options, but do not solve all the way for y. There were a couple of questions like this on the assignment, and a lot of you took the square root. And if I recall correctly, not a single one of you used a plus or minus sign when you took the square root to solve for y. The more simplifying you do, the more chances you give yourself to make a mistake. Do not take the square root to solve for y. Just leave it. This is perfectly acceptable. And to be perfectly honest, that's what I would expect to see from you, because the more work you do, the more chances you're giving yourself to make a mistake. So don't do it. But if you do want to get rid of the fraction, you could multiply everything by 2, or you could multiply everything by that common denominator of 6, or you could get the y squared all alone, but do not take the square root. Don't do it. Question 5, another differential equation. This time we have a particular solution. An initial condition was given. Starting off by separating my variables, multiplying both sides by dx, and then letting u equal that exponent, that negative x squared, and then compensating for that extra negative 2. So we pull that negative 1/2 out front. The integral of an exponential is itself, but when the base isn't e, you divide by the natural log of the base. So we've got our negative 1/2, we divided by the natural log of the base, times the exponential itself, and then our plus c. Here I'm subbing back in for u, and then I'm subbing in that initial condition. So y was 0 when x was 1. So I did 1 squared multiplied by negative 1, simplified that. And then 5 to the negative 1 means it goes into the denominator and becomes 1/5. So I multiplied it by the 2. Here I just had added that term to the other side to get c alone. So then here is my general equation. Some of you took this because it had a negative exponent and put it in the denominator, and that's fine too. I will accept both answers. You can leave that in the numerator with the negative x squared, or you can bring it to the denominator. Question 6, another one with an initial condition. Here is our differential equation. So I start by separating my variables. I multiply both sides by dx, and I divide by e to the negative 2y. Now we don't exactly know how to integrate e when it's in the denominator, so I can pull it to the numerator and make that exponent positive. Integrating e to the 2y, you could use u substitution and let u equal that 2y, but I just kind of undid the chain rule. So the integral of e is e. If I took the derivative, I'd multiply by 2. So when I take the integral, I divide by 2. Over here, this is just your basic power rule. Integral of x is 1/2 x squared, and integral of negative 5 is negative 5x. Next, subbing in that initial condition. So my x value was 5, so I put a 5 everywhere there was an x, and my y value was natural log of 5. So I had 2 times that natural log of 5. Simplifying, I went ahead and used my power rule so that my e and my natural log could cancel. So I took that coefficient of 2 and made it a power on the 5. So now those cancel, leaving me with 1/2 times 25, or 25 halves. Simplifying over here, and then my 25 halves cancel. I could subtract those from both sides and then add the 25 to both sides. So my c value is 25. Subbing that back into my original equation, leave it alone, or if you really want to get rid of those 1/2, you can multiply everything by 2. So that's my second equation there. Question number 7, another differential equation with a particular solution. Start by separating the variables, dividing by 3y and multiplying by dx. So when we integrate with the variable in the denominator, that does give us natural log. So I left that 1/3 and the 1/2 as a coefficient. Notice when I got natural log, I put absolute values around both of my variables. And then we've got our plus c, which we will solve for. But before I do that, I am using that property where if I take e to both sides, it gives me a constant multiple. So I did show my work here if you needed a reminder of where that came from. So when I took e for both sides, as a reminder, this is that property of exponentials. If you have e to a power plus a power, it came from a power times a power. E to the c is just some sort of new constant that we are multiplying by our x to the 1/2 once the e and the natural log cancel. So that's where I got this y to the 1/3 equals c times x to the 1/2 from. Subbing in those initial conditions, y was 64. The cube root of 64 is 4. 9 to the 1/2, the square root of 9 is 3. Solving for c, and then again I can sub that back in. Or if you want to cube both sides, you can. But again, Don't do more work than you have to. I will accept this answer. The more work you do, the more chances you give yourself to make a mistake. Number 8, I just sketched a graph through -3, -1 because the second graph was a point of your choice and I didn't know which point you would choose. So lots of different options. If you do have a question on what your graph should look like through your point, I'm happy to go over that with you. But through 3, -1, that was our starting point. And as a reminder, you want your line to be parallel to those little slope lines. So off to the left here, it's increasing, and then it slows down, the slope slows down and then becomes horizontal, and then it approaches this kind of slant asymptote here. So that's the general shape of the graph through that point. Number 9, sketching a slope field. I did show all of my work. In this case, if you didn't, that would be fine because I know you know how to multiply x and y and then make it opposite. So really what I'm looking for is the general shape of your slope field matches mine. I'm not going to be looking for any exact values, just that it has the same shape as my slope field. And finally, one more differential equation, rewriting that y prime as dy dx and separating our variables. So I multiplied both sides by dx and divided both sides by y. The integral of y is that natural log of the absolute value. Over here, we just have our power rule, and then solving for y using e, it's that same concept we used on number 7. So that plus c becomes a constant multiple when this whole expression becomes a power. And then we've got that e to the 5/2 x squared. So that is our final answer. As always, if you have any questions, please reach out to me and let me know.